Hello and welcome to the fourth episode of the MedUpdate podcast. Here we discuss new updates in medicine with experts of their field. My name is Zehran Punika, your host and soon a second-year medical student at the University of Lancashire, formerly known as UCLan. I am joined with my great friends Fahad Sultan and Taha Kazi, and our special guest today is Dr. Matthew Dickinson, who is a senior lecturer at the University of Lancashire School of Engineering and Computing. He has a PhD in tribology, which is the study of friction, lubrication, and wear of interacting surfaces in motion. He now applies this knowledge in assistive technologies and specializes in wearable robotics like exoskeletons. This podcast has become a bit of an annual event at this point. As a result, I am delighted to announce the MedUpdate blog, where we will publish articles frequently, so keep an eye out in the video description, our community tab, about section or website that will have a link to it as soon as it's live. Now let's get on with the podcast. So it's great to finally meet you, Dr. Dickinson. I've been hearing a lot about you from your students. Could you kindly introduce yourself for the audience, please?
Oh, yeah. So my name's Dr. Matthew Dickinson. I've been a member of staff and a student, including at the university, for 17 years. I predominantly focus all my efforts in mechatronics applications, but my real expertise and focus in research and application is exoskeleton technology.
Great. So we can start off with Fahad with his questions.
All right. Thank you, Dr. Dickinson, for that introduction. My first question is to do with exoskeletons. So, what are exoskeletons and how are they different from prosthetics, in your opinion?
So good question. So obviously prosthesis is the design of an attempt, and I like to emphasize on the application of attempt to replace limbs. So for example, if we were doing a prosthetic arm, let's say just from elbow to hand, we'd have to design the forearm, we'd have to design the hand unit, and have to power towards it. This would actually try to offer some level of replacement, but let's face it, it's a human hand. It's never going to be as good as the human hand. However, what the exoskeleton does is this offers a wearable assist process. So let's say, a great application, a great example of this is a crutch. If we're injured and we can load some of that loading that would go through our ankle, and we can load it by leaning onto that crutch, and that allows us to have that aid and assist. Now, if you're wearing an exoskeleton, while in that process, doesn't necessarily have to be for rehabilitation. If you're holding heavy items, what this should be able to do is relay some of that loading. And then if we apply motors into this, a method of actuation, we can then provide assistance around the joints to allow people to move a little more freely in that process. That's my best description.
Okay, that was very interesting. Yeah. So my next question is that when researching about this topic, I came across soft exosuits as an alternative category of exoskeletons. So could you tell me a bit more about them and how they compare to typical exoskeletons?
This is, yeah, you've obviously done your homework. This is a really extremely good topic. So one thing I didn't do in the introduction is I didn't explain that I do an awful lot of work with the ASTM, which is an international standards committee. Now, what we do is we bring all companies, all academia together to discuss the safety of application for these types of devices. A really hot topic of discussion is this very question. Exoskeleton. If we think of exoskeleton on an insect, it's an external structure around the body to enable them to live in a process where they can load on and remove load. Same process. We're essentially doing biomimicry on the human to try and see if we can do that process. Now, when you get onto exosuit, this is a really interesting topic of, does it even exist? Does it even actually exist in the process? So the exosuit idea is large elastications around structured areas. So a great one for this is the back. So let's say, for example, you're wearing a belt around your hips, or let's say a pair of shorts. Then if we were to put, I suppose a great example would be like dungarees, where we have elastication over the top. But if you think of that, these are then held in position. And then when your body moves into a bending position to grab something, these elastications are then loaded. So then what it's allowing that to do is use that in the aid of lifting something back up. It's providing an assist in that process. Now, the real discussion is that an exosuit or is that a garment? Is that a sophisticated fabric? Because they both serve the exact same thing. Now, on the international standards committees, students. So some of the students that I have, they're actually involved in the discussion of, is it a exosuit or is it a fabric? So we've even been able to reach to some of the medical industry who actually already make braces around the braces, and we're really trying to feel our way through it. So the straight answer with this is the difference is an exoskeleton has a hard-based structure around it, and at the moment, because I have to be careful on that one, at the moment the exosuit is a soft-based solution which is attempting to mimic muscle contraction. And that's in short of what that will be doing.
Yeah, thank you for that analogy as well. I think it makes it a lot more easier to understand, at least for everyone else. My last question, at least for my section, is that what groups of people will benefit from these exoskeletons? And could you give a few examples of how they could be benefited?
So, large, vast area of this. So you've got different areas. So my company, for example, what we've been looking at is we're actually not focused on rehabilitation right now. We're actually focused on assist and prevention. So an interesting thing was, and I'm going to try and keep this short, in 1859, the very first exoskeletons designed by a Russian scientist. This then goes dark for many, many years. Then the 60s, the American naval research and a GE then make the world's first fully powered exoskeleton. What they realized was that this was great for manufacturing. What's interesting is exoskeletons were originally designed for manufacturing and the moving of load carriage, as they say. Then what's actually started to emerge is new techniques for manufacturing, new garments, new fabrics, new plastics, easy to make stuff. Now what's getting exciting is we can now do EMS, so your electromuscular stimuli. Now I know you guys, you'll be like, ooh, that's a itchy one, is that? Because it really is an interesting topic of that. Can you stimulate muscle groups to react under certain states? Now, if you do get chance, Google Parkinson's disorder and exoskeleton. It's not straightforward answer, and it's not an instant answer. But some patients wear EMS exoskeletons, and you should see the results. Mind blowing to see the shakes have just been brought down to a gentle stammer, if you will. The other side of this is those who go and protect us. So from police through to fire through to military. So for example, a great example of this, and then I'll finish with my answer to the question is, if you think of firefighters, if you think of Grenfell Tower, when they actually came in, you've got full BA kit, the breathing apparatus. They can be ranged between, I think it's between 25 to 30 kilos in some case. It's a lot of weight. Then they're traveling up the stairs. They get to the top of the stairs. The metabolic cost of getting up there gives them around, I think it's around 15 to 20 seconds to get around to try and save as many as they can. By wearing an exo, in this case, you're going to be able to get people to the top of that stairs, giving them 5, and in some cases, maybe even 10 seconds greater. So in this case, what you'll end up doing is saving more lives in the process. So when you think of people who are paraplegic, who are now getting the benefits of the wearable robotic structures, like, if you've not seen it yet, the Korean F1 design, which is a robot which will walk up to the user, it will wrap itself around the user, and then the user walks off, enough to bring a tear to the eye. right through to the Moashi stuff. That we've got such a large range of exos that are just providing so much. So in short, everybody's going to get a benefit of it.
That's very promising to hear, especially with the future of exoskeletons and exosuits.
100%.
My questions are finished. I'll like to pass it on to Baha.
Thank you for the amazing set of questions, Fahad. So, Dr. Dickinson, let's bring about your entrepreneurial side. Could you tell us more about your startup, Viking Exos, and what it aims to deliver for the public?
So yeah, this actually came about. So I've been working in this area for about 10 years. If you've seen anything before, how this came about is my actual PhD was based on Formula One technology. I did a lot on the way that materials interface with other materials, and then I finished PhD, and I was hungry to try and get a feel of where I should move. And I'm a firm believer in public engagement. I got involved in an event called Primary Engineer. If you guys ever see it, the idea is you go out to schools and say to hundreds of kids, if you're an engineer, what problem would you solve? And my role in this was I was to review some of the results, and then I was to try and make some of the examples. One year we had a young girl. She came in and said, why is there not special shirts that children can wear to help them move? And I knew she was talking about an exoskeleton. But then when I looked under the surface of all this, it was like, you know what? Yeah, this is absolutely true. So we built, well, now I built an exoskeleton based on a mechanical engineer's perspective. So in other words, lethal. This thing should never have been worn, should never be touched the human body. But we learned so much. This single structure we learned so much. We went back to the drawing board, and then other people in the university, so for the biomechanics department, Professor Jim Richards guided us in the right direction in which way this would go. So I started working with some of his team, and we went back to the drawing board. Then the exciting stuff started to happen. We started to come away with methods and what would work better. We as engineers learned so much because we were learning more about the biomechanics of it, about what makes that human tick and what's the best way to approach it. And then what we've done is we started into devising different exoskeletons for manufacturing and prevention. Personally, right now, the human body, it's so delicate, and where we are as a company, we're not ready to start supporting somebody who's injured, because I think the body needs a lot more than what we can offer right now. However, prevention and assistance to aid people who are in manufacturing right through to support in emergency services, I think is huge. So what we did is I was a little bit rogue. And after many years of devise, what I did is I applied to the UKRI, so UK Research and Innovation, for some funding to see if a company, UK's very first manufactured exoskeleton company, had legs. So I was already doing work with the international standards. Then started to bring it all together. And then what I thought was, could I actually, would they like it? So a thing that's called iCure, they have these multiple step processes. The first step process was 6 months. They kind of review what you're doing and go, that's great or that's awful. What I realized in myself, and if you guys have ever been involved in business development, sometimes you just like spring into action. So definitely, if you get a chance, do a short business course. Insane. Anyway, I get into this. They then love it. They then send me around the world last year. So I was traveling 6 months. I traveled across the US. I traveled to Dubai. I traveled all over the UK as well to speak to people about exoskeletons. Realize now what we were doing is I actually genuinely thought, and I know this makes everybody cringe, but I actually genuinely thought I was making exoskeletons for every service person. Every person who was going out to battle, I thought we were making, and it turned out I wasn't. It was rubbish. I had the privilege of sitting in a NATO meeting, and this is a genuine story. So I'm sat in a NATO meeting, spoke to a special forces guy, and I said to him, I said to him, if I was to make this exoskeleton for you, would you wear it? And he said, this is crazy interesting. He said to me, if I was when I train hard. I train to be fit. And it makes me cognitively feel safe. He said, if I wear that, I'm going to feel endangered. That's going to get me injured. And I was like, oh my God, this isn't going to happen. Then this woman came up to me, roughly about 5'7", about 90 pounds. And she said to me, when I'm loaded, I'm about 110. She said, I have one side arm on the side of me. She said, but when I'm on the battlefield, I'm the first person they want to kill. And you kind of go, that's scary. That is terrifying. She said, if you can help me move some people off the field to save their life, where do I sign? And then we realized this isn't about weapons. This is about saving lives. So we're actually targeting that. So we actually got a range of how we're operating. We came back, we presented about the application, we presented about the positivities of where we were going. The UKRI loved it. And I do a lot of my family genes. And one thing I was sick of people realizing is that everybody from the South always get all the good stuff. I wanted people to realize that we're Northern. And because we're Northern, we are just as good of innovators. So Viking Exos. So Viking was born because of it, because they were the Northerners. And obviously most Northerners actually have Viking heritage to themselves anyway. So I wanted to send a message of that, yeah, we are the first. Yes, we are Northern and we are innovators and strong in the process of that we do. So Viking Exos was born in that process. So it took its time, took its real close time in it. And now we have our first signed up company who's going to be using one of our exoskeletons on their manufacturing shop floor. And then everything else, we have a few more exoskeletons on the go too. So it's super exciting. And you can kind of see in the story that I've told you, I kind of fell into this. I didn't realize, and you kind of learn so much about who you are going out there and saying, this is my tech and this is what I can do to help.
Thank you for that amazing answer, Dr. Dickinson. Obviously, with every company, there are ups and downs. So with Viking Exos, what lessons have you learned from running it, would you say?
It's a lot. So one thing I would recommend is I don't know if you ever read the book The Diary of a CEO. Everybody knows Steve. I always forget his name, but he is insanely good. And one thing he always talks about in there is sometimes you love what you're doing so much you can become blinded by what you need it to be. It becomes your brain, baby. I would always say try, and it's a hard try, to just remove some of the emotion from the investment that you've got. Because as a friend of mine says, you've got to be ready to hear that your baby is ugly. And then to really address that is huge and it's massive. And you can learn so much in that process. But that has been my biggest learning side of don't take it too hard. Don't take it personally. This is business in the process. And any criticism you can get, one of the greatest things you can ever do is take a criticism and make it something good.
Amazingly said. So I've been reading about machine learning algorithms. Could you expand on how AI is being used in your exoskeletons as an aid?
Yeah, this is really fascinating. So at first and it sounds horrid to say, I've always been, I want to stay away from AI. And it's just because you're carrying extra stuff on board.
Yeah.
What happened is one of our exos that we've been working on, we call it the sensorless exo. So we can control an exoskeleton with no sensors on the body at all. Zero, in fact. And it's left everybody going, that makes no sense. But it genuinely works without any sensors on the body at all. We realized quickly though, some of the things that you could do, you could trick some of the things that we have with it. So it's great. But as you guys will know, if you're wearing something and something can be tricked and a misfire could happen, you could potentially injure muscle groups dead easily. So what we're now trying to do is we're trying to use actually a combination of I don't know how much you guys have done, but Olama, the server for smart control systems, we're actually bringing in ChatGPT, DeepSeek, and also part of Gemini, and running them on an Olama server so that we can control what's going on with it. And the idea is the system is going to be just checking for what's going on. If it sees something that's irregular, it's going to try and just chop off that threat. But at the minute, I'd love to say it solved everything, but it's still not solved it perfectly. So it's not quite ready.
Okay, that's good to hear. How would you tackle the main obstacles of the use of exoskeletons in the treatment of patients, such as cost, the weight of the machinery itself?
So doing the work that I've been doing with ASTM and everybody on board on the ASTM side of things, this is one of the biggest topics in the world. It's how is this going to get adopted? The tech at the moment is crazy expensive, and there is a lot of high cost behind it. The work that's been done, you cannot argue. Phenomenal, some of the stuff that's going on. But moving this forward, we need to be able to really look at manufacturing techniques. When we consider from because they call it F48 from the ASTM side, when we're considering about how this has been addressed and how this has been moving forward, we really need to now look at the biomechanics people are inputting, how they are actually testing this. We take this testing and we try and influence the design process for it. This design should then flood it out to the likes of people who are 3D printing, the likes of people who are doing composites. And if we can actually find a common ground, what we should be able to do is find the most cost-effective way of manufacturing exoskeletons, but keeping the cost down. Just because, for example, if we were to consider, say, one of our arms, for example, I can scan your arm and I can actually build you an exoskeleton to fit to you. But the cost of manufacturing to you and manufacturing to a group is huge. And I think we're only ever really going to hit that point and when we can actually tailor an exoskeleton to fit a person. And the only way we're going to do that is if everybody sits down and kind of says, right, this is how we solve it. Because at the moment but it is still early tech. It's not like we've not got people who aren't wanting to, but it's just because we're just at that position, that's all.
Yeah. In terms of the materials and stuff, is there anything you do to make the exoskeleton more lightweight?
Yeah, so the early days of stuff that I was doing, and I know some of my friends that I have on at ASTM from different companies. Personally, myself, what I was doing is I looked at the standard 3D printing. So we were like, you know what, we can cure cancer with 3D printing. But then what we did is I have a PhD student who's studying 3D printed materials and looking at sweat and what happens when your sweat engages with the 3D printed material. We then realized what was actually happening is the sweat from your body was feeding the 3D printed material and it was growing a lot of bacteria around it. So we realized then just 3D print is not the answer. So then what I started to look at was 3D printing and then coating in composite material. Don't get me wrong, super strong, but really, really uncomfortable. When you actually have skin, if it touches the 3D print composite material, it's not pleasant at all. So we then looked at creating molds. Now, where we've been at the moment, because we're still doing this, where we've been at the moment is using a technique known as carbon forging. It is a mint technique. So what we'll essentially do is we'll grind down fibers. Now, an exciting thing for me, the theory of carbon forging, we can take carbon fiber parts, we could grind them into bits, forge it, and it would still make a good exoskeleton component. And that means possible, and I need to emphasize possible, recycling. And an element of recycling, so the carbon impact of that is quite good. But again, we're still early days with that. So yeah, I have 1,000 examples of exoskeletons that were really cool and ones that really weren't.
Yeah. So everybody fears that exoskeletons, if they start to be introduced to society, malfunctions can happen. So are there any key safety features in the latest exoskeletons that help tackle this?
Yeah, I mean, again, this is an incredibly good question. So what we actually face when we're referring to safety. Now I'm going to quote a friend of mine who's from another company completely, but he does stuff on carbon fiber. When we sit down in the ASTM groups, what we're essentially trying to do is we are taking, I mean, we love doing this. I mean, hell, I would sit here all day and attach stuff to myself just because it's so much fun seeing what will work. But what we do is we sit down as companies, we sit down as academics, we sit down as futurists and visionaries to try and look at, we want to do this, but we want to do this safe. So what we do is we introduce consensus. This brings companies, academia together to kind of say, this is how we do it. This is how we know it's safe. So the standards that we write for ASTM are actually based around ensuring that safety protocol is met in every single iteration that we meet. So some exoskeletons, for example, based on the ASTM recommendation, are designed to fail in certain states. They're designed to deactivate in certain states. And some of the testing protocol that's come from the result of an exoskeleton is designed to ensure that if somebody puts it on, they use it right and what's recommended to use it right. The technology being so new but accelerating to such a degree, safety is a key element, and that's why I meet with everybody from ASTM twice, maybe 3 times a week in some cases for this particular reason.
Perfect, thank you. So now I'm going to move on to Zahran, who will talk more about the medical side of exoskeletons.
Hello. I really enjoyed listening to your stories and explanations. They're very well detailed, and I don't know. It's just the way you explain things is very captivating.
No, I'm glad.
Because
I'm glad. I can talk forever on this, but yeah, go ahead.
I did want to talk a bit more about sort of that origin story of sorts of how you started out with Viking Exos. Specifically about the 6 months you spent with Christina Marshall, a student at Sir John Thursby Community College at that time, in the design, development, and production of an exoskeleton for those with spinal muscular atrophy, or SMA, which was initially intended for children. And just to briefly explain what SMA is, it's a rare genetic condition that leads to progressive muscle weakness and therefore movement. And it's from a mutation that occurs in a gene called SMN1, which causes a reduction in the production of survival motor neuron protein, or SMN, resulting in the death of motor neurons and therefore the muscle weakness. And as that's because SMN protein is necessary for the survival of those motor proteins. So I wanted to ask Dr. Dickinson, from this experience and others you've had, how you think exoskeletons can help with people suffering from chronic conditions like this that cause muscle wasting.
So yeah, I mean, so again, great question. So when I first got involved on the origins of this design, we sat down and young Christina. So let me just paint her picture. She was a high school student. She was kind of convinced that she wasn't going to end up to be anything any good. But you know, when you speak to someone, you kind of go, I can see the mind just exploding with excitement of where she could go. So I actually sat down with a teacher and just said, you know, this is a great idea. You should be proud of what you've done. So she explained to me that her cousin has SMA. She explained the process. She'd seen that degradation, that process. She explained to me with it. Now, when I first approached this, I will kick my backside in this case. When I first approached this, I kind of approached this like, yeah, it should be fine. We'll just make one, just stick it on. We made it and then realized so much with it. The SMA process, the process of any muscular disorder in this case, is an interesting one. Post making what we now call Marsha. We call it Marsha just because it was the exoskeleton we did for Christina. After post making Marsha, we realized that exoskeletons are interesting. Now, if you're talking atrophic states for somebody who's actually using these daily, I've very little effect on that state, just because people are so active using this stuff. All they'll do, I mean, I spent time with a Marine, and all he ever said was, if you're going to give me a chance to use my body more, I'm going to push it to the limit. But if we go roll this back to somebody with muscular disorders, what we do is we try to find the sweetest spot possible. Now, the SMA jacket that we produced in this case, what we did is we made it, and then it sat on ice. It became the big learning thing for us. That's why at the minute I actually gave her away in the end, and I gave the exoskeleton back to primary engineer, where to this day the exoskeleton still stands. But yeah, we'd learned so much from doing this that recently, without digressing too much for an NDA, we've been working on an actual a jacket in this case for a well-respected charity, and we've learned so much. Now, I personally believe that the muscle and the way that we address muscle, we need to be able to again allow that muscle to excite, allow that muscle to extend and contract and still operate, but don't take over it completely. We take over it completely, and you guys know the degradation state, the atrophic state will just devour you like it does on an astronaut within a couple of weeks. So what we need, and as we move forwards with these things, we just need to keep a nice sharp eye on a person using these and ensure that there's not something that's a knock-on effect. And don't get me wrong, I'm sure anybody who listens to the podcast will kind of say, well, we could use EMG sensing. We could check the sensors as we're going through. I would still argue that a professional surgeon or a nurse to just check on muscle groups, ensuring that they're not moving into a bad state, would still be needed, even if you've got sensors on board. I think all the sensor does is it helps a professional do their job even better. So when we refer to that, that would be my best answer.
Right, thank you very much. I know there's a bit of a move from joints to muscle specifically, right? Just to prevent or maintain the muscle. And actually, there was one situation when talking to your students. It was at I think it was a society event. I saw a green exoskeleton, and I heard it was one that you made. Do you recall that?
Yeah. Yes. So, so this one is what we call when we attach it, we call it. It's actually attached to what we call Little Timmy. So we just do it. It's just something I've always been brought up with. You personalize things, and this was brought on the idea of that exact approach. This is really, at the moment, the structure of that is really based on being more of a brace, but technically still an exoskeleton. But what I mean by this is we weren't really aiming to offer an assistance. We weren't offering an actuation. So what this was designed around the idea of is this actually came from a mum. So they were coming round to actually look at the labs. And she said to me, she said, my daughter sometimes has to go to school with a rucksack on, and it's so big, it's bigger than her. And it got us thinking about what if you could put on a rucksack and you could offer a bit of an offload in that case. So the prototype process of Little Timmy was born. But Little Timmy in this design was not powered. We'd gone back to mechanical, and we'd gone back to just creating. Best way to describe would be a crutch that could move around your body. And that design really sparked some of our first responder stuff. We were able to look at that and kind of go, oh, we could do this. Oh, we could do that. And through that design, we got to one of our niche design pieces, which is, and this is fascinating. I was testing on myself with others in the biomechanics lab.
Yeah.
I've got EMG sensors all the way down my body. So I was testing the first leg exo that we had. And you know what it's like? You do the baseline. So we did the baseline test till we got all the muscle groups. Then I put on the passive side of this. So if you think a little Timmy, this is just the legs I'm wearing, but it's the adult version of that. Then I put that on and I walk up and down, and then we noticed between 5 to 10% reduction of loading around the joints because the muscle groups weren't needing to fire as much. The strain gauges in the floor were actually picking up of that load distribution state. Honestly, you know, when you think we've nailed it right now, then we turned on the full active side of this. When we turn on the full active side of this, the EMG muscle results showed 4 times greater operation than what they should have.
Wow.
What we realized is my muscles had moved into rejection.
Yeah.
Straight away, you could see the muscles going, why are you helping me move? What is happening? So then we went back to the drawing board and we came up with a new technique of controlling an exoskeleton where if you're not carrying anything, it just turns itself off. If you go to pick something up, it turns itself on and offers assistance. So somebody hates me saying this, but it's like a stop-start exoskeleton. So what we done in that process is we just realized that when we're testing on the body, offering these methods for support, we can actually try and minimize the level of time that the body needs it. And that's what our patency sits in.
Thank you very much. That is actually quite interesting. It looked quite complex, is it?
It is at first. And it was just because with the input of I should say Graham Chapman, who's the biomechanics side of all this, with input from Graham, we realized what worked and what didn't. And he was the one who kind of went, that's how the ankle works. That's where we need to look here. And yeah, it's been a real learning aspect to it. It really has.
Yeah, but it's always fun when it's out of your specialty, isn't it? Something new to learn with each
Isn't
project.
it?
Yeah.
Isn't it? Every day should be a learning day.
Exactly. I wanted to ask, like, from my brief research, I've actually been very surprised by the number of new advancements with exoskeletons, like the incorporation of AI, the new and different materials being used, and the technology that uses energy generated from the user's own movements. That's actually particularly surprising. I know it's used in watches, but I was thinking in
Yeah.
exoskeletons, that's actually very impressive. But I also wanted to know if you could shed some more light on these recent developments and others, especially relating to medicine, including the one that you were researching with the UK Space Agency, like you're talking about with the astronauts and preventing any loss in muscle mass, using exoskeletons to resist muscle movement. I'm very interested in that. So if you could tell us a bit more about that, that'd be great.
Now this came out of a great discussion. So obviously getting involved with stuff like this, you get to meet people.
Yeah.
So I managed to make a contact from MIT, and she was working with a real Dana, I can't remember her last name. And what they were doing is that this professor in MIT is just obsessed with exploring. She's like Wonder Woman. She's insanely good. And one of the PhD students I was talking about, and she was talking about deep sea exploration, and she was talking about the difference in pressure around the body. And I got into a discussion again with Graham, and we were talking about what if you were traveling. Now this came out where obviously we've now got a lot of the new space exploration stuff that's coming out from the UK.
Right.
We then got into a discussion about an exoskeleton is assistive, but what if an exoskeleton was resistive? What if it made this fire? Now, I do need to put a disclaimer. This does not aid the stress shielding problem. So the stress shielding problem of bones is still there. It's still going to happen. What we were targeting here is could we make muscle groups still fire? And we realized with a microcontroller using an AI-based system, we could control how much assistance or resistance the exoskeleton would offer in different states. So if you landed on Mars, you could actually get it to control and aid in one state. If you were floating around in the atmosphere outside of the Earth, then we could offer it to make a resistive state. So what it would do is it would remove the need for the gym that's typically on board on most space shuttles.
Yes.
The interesting side of this as well is when it comes to 3D printing side of things, there's a lot of advances now looking at using materials outside of the world and using that for 3D printing. So then it got us to thinking, is if something fails, you could just print it and replace it in that state. There'd still be problems. There is always still problems. In this process of setting up Viking Exos, a lot of other friends that I've met on the journey, I only bring this up because you brought up the kinematics, the kinematic energy generation.
Yes.
When I was in California at a medical event, one of the friends that I had who was on the IQ program with me, she was working for Oxford, and they devised a pacemaker system which sits obviously for what it does, but what it does is it powers itself from kinematic motion. And it didn't need, and you look and go, when I said that to her, I went, how close are you as far as, because you know what it's like, you speak to a lot of people and go, yeah, in theory, but they'd already done testing, they'd already done baseline testing, they got some preliminary tests completed, they got some sample tests done, and this thing was working and is still working. And that's an exciting concept of that this is on the horizon to appear at some point soon.
That's more than promising then.
Oh my God, yeah, absolutely.
Thank you. That was great. Just to end off, actually, where do you see the future of wearable robotics in the next 10 years?
So what I can tell you is Horizon this morning just put out a big talk about exoskeletons and wearable technologies and robotics and the way that humans interface. We will start to see, and this is a bold statement, I think in the next decade, we will start to see people wearing exoskeleton tech, but the exoskeleton won't be just offering assistance to you. It will become a controller. It will become a platform of interactivity. I think this will allow employees to make sure that somebody's healthy when they're going into a dark area, for example. We will also see the IoT element of this, the Internet of Things piece of this. So, for example, everybody remembers the porter in the hospital. Everybody's been to hospital. You've had some guys had to push you up and down. We're going to see the point of where that guy, what we once saw years ago, is going to be assisted by robots. That's going to help them move the bed. We're going to see surgeons that are going to have wearables attached to them that are going to be able to just call Da Vinci's in when needed. We're going to see a real opening excitement towards this. The only reason I say this is I've seen other universities around the world actually talking about how they can move to the next phase to do this. So the reason I'm saying this is it's people who are already thinking about this. It's not a pipe dream, which is crazy exciting for me. When we talk about prevention, I firmly believe that we're going to get to non-Newtonian materials. So we're going to get to a position where our shirt will be okay. And then when we need it will stiffen up to support our bodies in the most present states, or it will give us some assistance when needed. And that's a crazy exciting thought for me as well.
It'll be a lot more convenient, a lot more comfortable.
Oh my God, yeah.
Rather than a giant metal pole on the outside of your leg.
Oh my God, yeah. Yeah. Oh my God, yeah.
Yeah, that's something definitely to look forward to. I definitely need to watch that documentary as well about Horizon.
Oh yeah, all of it at the minute. The hot topics of it, it's huge. There's just so much going on.
Yeah, it's great to hear. Did you have anything else to add? Anything else that you'd want our audience to know about?
The only thing I would add is if any of the audience, if anyone would ever want to get involved in discussions about exoskeletons, in discussions about the way that standards are, and you're interested, do reach out to ASTM student membership. You are able to become a student member, and you can actually hear and get yourself involved in what's going on. It sounds really strange at first, but until you've actually experienced these discussions, you never really appreciate the level of work that's going on already. But I think that's it. Other than that, this has been awesome. Thank you for having me on.
Thank you very much for joining us.